Here we are at problem 2C from our 2.1 number 2 set of notes. We're asked to find the average velocity between this time 1.9 seconds and time t is equal to 0. So again, we're referencing Mr. Splash, and luckily we already know what the position for him when he is hit 2 seconds, and that is in fact 0. He is pretty much in the pool at this point, or at least hitting the pool. But we have to go ahead and find out what is his position at 1.9 seconds. So we're going to go ahead then and throw in that value into the function. We end up with 64 then minus 16 times 1.9 squared, which just comes out to be 64 minus. And so when you throw this into the calculator, you end up with 57.76. And then going ahead and subtracting these two, you end up with 6.24 feet. So he is 6.24 feet up in the air at 1.9 seconds. So he's pretty much just about to hit that splash with the pool. Now let's go ahead and find then the average velocity with this information. So going ahead and throwing in our values, we can go ahead then and throw in 6.24 minus 0 over our 1.9 minus our target x value 2. So again, this was our target y value, target x. Other point right here. So it looks like it comes out to be 6.24 over negative 0.01, which actually then just comes out to be 62.4 feet per second. And there's still that negative there. So he's going down 62.4 feet per second. So he's actually traveling pretty fast, you know, when he hits this pool finally. And this is a pretty decent approximation for that. Now this kind of leads us then into the definition of the instantaneous velocity, and we've kind of already talked about secants and how they relate with tangent. Pretty much as you get closer and closer and closer to your target point, your secant actually then starts to then become closer and closer and closer to your tangent, or that instantaneous velocity. And pretty much what we can then do in terms of this situation, in terms of any situation I should say, is if we're trying to figure out the actual velocity, the instantaneous velocity at this particular a value, so that's kind of that target time that we're hoping for, then we have to take the limit as h goes towards 0. In other words, we are getting closer and closer to our target time. In this case, we were getting closer and closer to that target time of 2. Well, with the previous examples, we saw this one where we were 1 second difference. Here we were only 0.5 second difference, so a little bit smaller. Here we were only 0.1 second difference, getting even smaller. These differences in the times are our h value, and it's our hope that that h is going towards 0. In other words, minimizing the time for that. Of our function, so for our position, it's going to be our target time plus whatever distance we are away from that when we throw that into the function, minus the target's position, so S of A, all over our our other point with that distance in mind away from our target, minus our target, which then just comes out to be the limit as h goes towards 0, just simplifying this. All over h, so pretty much just these a's canceled. And so pretty much what we're seeing is that our velocities actually then translate over in terms of this limit, and then we could find the instantaneous velocity at a particular point, A. And again, we do have to make sure that the limit does in fact exist to begin with to then be able to determine that instantaneous velocity. And the speed, this is actually pretty important, the speed is the absolute value of that velocity. So for example, if we were just looking at these speeds, yes, it was negative 62.4 feet per second for this example, because he's falling down, but the speed of that would just be 62.4 feet per second. So again, speed is how fast you're going. Velocity actually measures two things, your speed and also direction. And as you can see with the direction, we see that he's negative. In other words, he's falling. So that's the kind of the difference between velocity and speeds. The speed is just the absolute value, though, of your velocity. So again, though, that is example 2C from our 2.1 number 2 set of notes.